Module 4, DNP3 Data Model, Objects, Groups, Variations, and Point Indexing. 4.1 Philosophy of the DNP3 Data Model. DNP3 is fundamentally a data-centric protocol. Its core strength lies not merely in message transport, but in the standardized representation of field data across heterogeneous devices and vendors. Rather than transmitting raw bytes or proprietary memory maps, DNP3 defines a formal data model that ensures semantic consistency, predictable parsing, interoperability across implementations, long-term maintainability of utility systems. Every piece of data exchanged in DNP3 is expressed as a typed object, governed by strict encoding rules. 4.2 Concept of Points and Point Indexing. Logical point abstraction. In DNP3, physical or logical measurements and controls are abstracted as points. A point represents a single data element such as a breaker status, a measured current value, an accumulated energy counter, a control output. Each point exists within a logical array corresponding to its data type. Zero-based indexing. All DNP3 points are identified using zero-based indexing. The first point in any data array is index 0. Subsequent points increment sequentially. This indexing rule applies uniformly across all data types and devices, eliminating ambiguity in point addressing. 4.3 Core DNP3 Data Types. DNP3 defines a fixed set of fundamental data categories aligned with utility operations. Binary inputs represent two-state conditions, examples open, closed, on-off, normal, alarm, used for indication and status monitoring. Analog inputs represent measured or calculated quantities, examples voltage, current, frequency, temperature, may be integer or floating point encoded. Counter inputs represent monotonically increasing values, examples energy, kilowatt-hour, volume, pulse counts, support rollover behavior. Binary outputs represent control points, examples trip, close, start, stop, executed through controlled command sequences. Analog outputs represent set points or control values, examples voltage regulation targets, flow set points. Each data type has a formally defined encoding and operational behavior. 4.4 Static data versus event data. Static data definition. Static data represents the current value of a point at the time of transmission. It reflects the present operational state of the system. Characteristics, snapshot of system state, returned in response to integrity polls, used to synchronize master databases. Static data does not imply change, it simply reflects what is. Event data definition. Event data represents changes or significant occurrences detected by the outstation. Events are generated when binary states transition, analog values exceed configured deadbands, counters increment or roll over, special internal conditions occur. Event data is the primary mechanism by which DNP3 achieves efficient bandwidth usage. 4.5 Event classes and prioritization. DNP3 categorizes events into 3 event classes. Class 1, highest priority events. Class 2, medium priority events. Class 3, lowest priority events. Class assignment is configurable and reflects operational importance rather than data type. This classification enables prioritized polling strategies, deterministic bandwidth allocation, faster delivery of critical events. Masters may request any combination of event classes during polling cycles. 4.6 Object groups and variations. Object groups. An object group defines the data category being transmitted. Examples include binary input objects, analog input objects, counter objects, control output objects. Each group corresponds to a specific type of data with defined semantics. Object variations. A variation defines how the data is encoded within a group. For analog inputs, variations may differ by integer versus floating point representation, bit width, 16-bit, 32-bit, 64-bit, presence or absence of status flags, inclusion of timestamps. Group and variation together uniquely identify the object format. Number 4.7 Flags and quality indicators. Many DNP3 objects include a flag byte that conveys data quality and source status. Typical flag information includes online-offline indication, communication failure, data restart condition, forced value indication, overrange or invalid data. These flags allow masters to evaluate trustworthiness and usability of received data, not just numeric value. Number 4.8 Timestamped objects. Event objects may optionally include timestamps, enabling precise sequence of events analysis. Timestamp characteristics represent time of occurrence at the outstation. used for fault analysis and post-event reconstruction, independent of polling cycle timing. Time synchronization mechanisms ensure temporal coherence between master and outstation clocks. 4.9 Objects as encoded data units. When data is transmitted, each point is encoded as an object instance. Objects include index information, flags, values, and optional timestamps. Multiple objects may be packed efficiently into a single response. Objects are self-describing through their group and variation identifiers, enabling robust parsing even in multi-vendor systems. TAP 4.Zen, reading and responding with objects. Read requests. A master may request data by specifying object group and variation, specific point indices, index ranges, all objects of a given type. Requests may target static data, event data, or both. Responses outstations respond by fetching requested point values from internal databases, encoding them as objects per group variation rules, packaging objects into application layer fragments. The master reconstructs and stores the data using identical object semantics. 4.11 Interoperability. Through the data model, the strict definition of data types, object groups, variations, flags, indexing rules ensures that independently developed devices interpret data identically, even when internal implementations differ. This data model is the foundation upon which DNP3 achieves true multi-vendor interoperability in utility automation systems.